Hello everyone, we are from Lab Group B128 and our team members are Shengyang, HongKabraAcharya and HongKabraAcharya. Today we will take you through our DSAI project. This is a brief table of contents on which we will be going through in our presentation today. Today we want to talk about the global increase in lung infections caused by the COVID-19 pandemic and specifically the rise of pneumonia cases. As we all know, the lungs are an essential part of the body and any infection associated with them should be treated immediately. Unfortunately, COVID-19 can cause pneumonia, particularly in severe cases, which has resulted in significant increase in pneumonia cases worldwide. With hospitals already filled with patients, it's crucial to detect and diagnose pneumonia in the early stages. Early diagnosis and treatment can prevent complication and help reduce the burden on the healthcare system. Pneumonia is an infection that inflames the air sacs in one or both lungs, causing coughing, fever chills, and difficulty breathing. According to WHO, pneumonia is the leading infectious cause of death worldwide, accounting for 15% of all deaths of children under 5 years old. Detecting pneumonia can be challenging as its symptoms can be similar to other respiratory infections. Even with the help of scans and data, doctors are subject to human error and may take time to diagnose pneumonia accurately. Misdiagnosis or delayed diagnosis can lead to complication and a further burden on our healthcare system. Early detection and treatment of pneumonia can help reduce the burden on hospitals and improve patient outcomes. This is where a model to detect pneumonia using X-rays comes into the picture to drastically improve the accuracy and efficiency of the diagnostic process. Our model saves significant cost and time, and it enables early detection, which can prevent the progression of the disease and reduce the risk of complication. Firstly, to solve this problem, we performed exploratory data analysis on our dataset. We sourced the pneumonia X-ray images dataset from Kaggle. One of the challenges we encountered during this project was that the size of the image for each category, normal and pneumonia, were different. To standardize the size of all images and improve accuracy, we decided to center crop all images to 256 by 256 pixels. This also allowed the model to focus on the most important features of the image while removing unnecessary information. In addition, we created a new directory to store our saved model and weights and continued with center cropping all our images to a square. After analyzing the data set, we found that it was highly unbalanced, with a large difference in the number of images in each class. This can have a significant impact on the performance of a model, and so we needed to address this issue. Ideally, we would like our train validation and test sets to follow 60 to 20 to 20 split. However, the unbalanced dataset made it difficult to achieve this. To balance our dataset, we opted to undersample our dataset by combining all sorts as one, then split them equally. We chose to undersample the images in the normal class to achieve a more balanced dataset. Even though we have lesser number of pneumonia images, we will be able to train the model with the same number of images in each class. The model will be able to learn better with the same number of images in each class. Now we have undersampled the dataset, let's have a look at our model.
We have used two machine learning models for this purpose. We have chosen to use DenseNet 1-to-1 as our image classification model because it is a well-known and effective model. Compared to VGG, DenseNet 1-to-1 is smaller in size, which reduces the computational load on the computer and makes the model more efficient. To customize the model to our needs, we will be implementing transfer learning by using the pre-trained DenseNet 1-to-1 model, which has been trained on the large ImageNet dataset. We are freezing the layers with the pre-trained model during the fine-tuning process to avoid overfitting. Then we'll be adding our own classification layers on top of the pre-trained model and training these new layers using our own dataset. To optimize the training process, we're using the Adam optimizer with a learning rate of 0.0001. The Adam optimizer is commonly used in deep learning and is similar to gradient descent, which we have learned about in class. The optimizer uses a moving average of the gradient and adjusts the learning rate of each weight parameter, making it a popular choice for training neural networks. By using transfer learning and a well-optimized optimizer, we can create an efficient and effective model for image classification. Also here, early stopping will be implemented so that time can be saved when there is very little improvement made to the model with each epoch. ResNet, short for Residual Network, was introduced in 2015 by researchers at Microsoft. The main idea behind ResNet was to use residual connections or skip connections to allow information to bypass one or more layers of the neural network. This helps to alleviate the problem of vanishing gradients and allows the network to be deeper, which often leads to better performance. We are using ResNet as a base model to see the differences as ResNet is more suited for more complex tasks, which we hope can spot the subtle differences between the two classes for a higher accuracy. When performing DenseNet for the following undersample data, we get this confusion matrix. Here, precision is a metric that measures the proportion of correctly predicted positive instances compared to the total number of instances that are predicted as positive by the model. On the other hand, recall is a metric that measures the proportion of correctly predicted positive instances compared to the total number of actual positive instances in the dataset. F1 score is a machine learning evaluation metric that measures the model's accuracy. It combines the precision and recall scores of a model. This confusion matrix is obtained using the ResNet model. As you can see that the accuracy of the models is high, but the precision and recall scores are low when they are undersampled, implying that although the models are able to predict most of the instances correctly, they struggle when it comes to identifying positive instances accurately. To improve the performance of the model, we plan to compare it with an augmented version. Now, as we have obtained the results by undersampling the dataset, let's have a look at what happens when we try to oversample them, as we believe that increasing the number of images through image augmentation can be beneficial for training the model. We plan to oversample the normal images by applying image augmentation techniques to match the number of images in each class. This will provide more data for the model to learn from, which may improve its performance. To oversample the normal class, we plan to use the sklearn library. However, increasing the number of images through image augmentation may also introduce problems. These are the results obtained for oversampled data using the DenseNet model. These are the results obtained for the oversampled data using the ResNet model. Upon oversampling, as you can see for both models, the accuracy, the precision and recall values decreased. Although we did not expect this may have been because augmenting only one class can affect the balance of the dataset and potentially decrease a model's performance. Moreover, since the images in both classes are similar, oversampling the normal images may not necessarily improve the model's performance compared to undersampling. This can be confirmed through the graph shown. We can observe that by oversampling our normal classes with augmentation, the validation loss and validation accuracy is drastically different compared to the undersampled model. The validation loss is very high while its accuracy is low when we oversample them, which should not be the case when we want our model to accurately predict the images. The same is applicable for the ResNet model. In conclusion, our machine learning solution is an effective tool for detecting pneumonia. During the project, we learned that augmenting minute differences in images of different classes can negatively impact model performance, leading to poor recall, precision and accuracy. Augmenting only one class can also affect the balance of the dataset and potentially decrease model performance. ResNet was also used as a base model to compare the performance with DenseNet. The main idea behind ResNet is to use residual connections to alleviate the problem of vanishing gradients and allow the network to be deeper, which often leads to better performance. Comparing the performance of both models, we found out that they perform similarly. And furthermore, we found out that undersampling and randomizing the dataset used to train and test can help to prevent biases. Moving forward, we recommend augmenting both classes, shuffling the images, and undersampling to avoid image repetition. Additionally, exploring other neural network models tailored towards complex image data could yield better results. We also shouldn't have undermined the importance of exploratory data analysis, such as calculating the mean of image arrays, which should have been explored further. Despite these shortcomings, our solution is reliable and effective in addressing one of today's most critical healthcare challenges. Thank you, and I hope you learned something from our presentation.